In this lecture, I am going to talk about how a nucleus becomes more stable, and how it gets to that point. When we talk about a stable electron configuration for an atom, we know that can become more stable by gaining or losing electrons to achieve electron configuration that's similar to a noble gas. And our nuclei are doing something similar. They're trying to gain or lose neutrons to be able to reach a more stable ratio of neutrons to protons that would mimic a stable isotope. And so the way that they're going to be able to do that we call nuclear decay. So we have an unstable nucleus that's going to decay to a more stable nucleus eventually, or hopefully. And what happens is when that change occurs in the nucleus structure to become more stable, the overall composition changes. And as it changes, those reactions that take place, they release tiny high energy particles or bursts of gamma rays from its nucleus. And so that's what radioactivity is. Radioactivity is those small little particles that have a lot of energy, or just energy waves, gamma rays specifically. And a gamma ray is going to be any burst of energy that is coming from an atom's nucleus as it undergoes a decay. And so in general with reactivity, we see that that these different particles that can be emitted or different amounts of energy will have different levels of danger because they will have more or less energy relative to one another. And so some of them won't be able to penetrate a 0.01 millimeter piece of lead, and others will be able to go through 100 millimeters of lead. And the higher energy, the higher the energy, so like these particles right here, gamma ones, the higher the energy, the more penetrating power it has. And this is just comparing pieces of lead, right? And so the higher the energy of the radioactive particle, the more lead it will actually be able to penetrate through, making it more dangerous. Okay. So we represent this in chemistry with a chemical equation, like we do our regular electronic-based transformations. And our structure for these is going to have the same overall structure. We have a kind of before and after with an arrow that tells us that we have reactants on the left-hand side and products on the right-hand side. And when we're looking at nuclear decay equations, those reactants are always going to be a nuclide, a parent nuclide, we call it. And they always form a product, that's what we call a daughter nuclide. So it's what is the new isotope or element that forms after the nucleus undergoes a transformation. And when it undergoes that transformation, it also always releases either a particle or energy or both. And that will be captured here on the product side. So we always have a starting isotope that splits into two different things, at least. Something that's a daughter nuclide, and then whatever small particle is being emitted as radiation. Here's an example of what we call beta decay. So we have our parent nuclide right here, which is our carbon-14 atom. Sorry. And we're going to structure our formulas not with chemical formulas, but now we're going to be using isotope symbols to represent these nuclides. So we have an isotope symbol for carbon-14. We have its mass number, and we have its atomic number, which is characterized by the number of protons. And it decays. It's going to release what we call a beta particle. A beta particle has a really negligible mass, and it has a charge of -1, which is basically the same thing as saying it's kind of like its atomic number, right? Because our atomic number in carbon, this 16, this represents the +6 charge of the nucleus. And the -1 charge of this beta particle is similar. And so we're basically tracking in this bottom row, we're tracking charge. And in this top row, we're basically tracking mass. And so we can take the sum of these masses and these charges, and they should equal what we start with. So I have for my mass, I start with 14 for my carbon, and my particle that's released has no reasonable amount of mass compared to a proton or a neutron. And so that means that the mass for my daughter nuclide can't change. It's still 14. For my charge or my atomic number, however you want to think about it, I start with 6. And I know that as a product, I'm going to be creating this -1 charge. Well, these need to balance. And so that means that as I create that -1 charge, I really have a charge then of 7 for my daughter nuclide. And this is really the atomic number, because this is characterizing the charge in the nucleus. And so that is characterizing the number of protons. And so that 7 is its atomic number, which if I go look at the periodic table, tells me the element is nitrogen. And so that's how we'll develop these nuclear decay equations. We'll have something that decays into two things, and we can determine what either the particle is, or the daughter nuclide, or even the parent with just any two of those pieces of information. So here are the radioactive particles you can see. So we have protons. We typically write these as a symbol of P with a superscript plus. And I tend to write the nuclear symbol this way, where we have a proton for the symbol with a mass of 1 and a charge of 1. You can also use a hydrogen as well, because this is basically a hydrogen. A proton is just a hydrogen cation. So if we're looking, these nuclear symbols are looking just at the nucleus, which can be a little bit confusing when we're looking at the chemical symbol for something, but we're only talking about the nucleus of that chemical symbol, because there's no electron on this one, it's just the proton. Neutrons are going to have a mass of 1, but no charge, right? And so we see our mass as a number 1 at the top, and our charge at the bottom is 0. And so this will be our symbol for neutron. Our electrons will have negligible mass and a -1 charge. And so we use an E for the symbol, and it's -1. So these are kind of our subatomic particles that we're used to. Now, we're going to look at the radioactive particles that can be released from the nucleus. So we have alpha particles. Alpha particles are essentially a helium nucleus. They are 2 protons and 2 neutrons. And so we can use either the symbol of an alpha, or we can use the helium chemical symbol. Just remember, there are no electrons. It's just the nucleus of the helium that we're looking at. And it'll have a mass of 4, because that 2 plus 2 is 4, and a charge of 2, because there's only 2 protons. And so this is our largest of our radioactive particles. It's like the largest chunk of stuff that could go flying out of our nucleus. It also has the least penetrating power because of that. It slows it down. All right, next we have beta particles, which we use this beta symbol here. And you'll write this as either a beta particle with a 0 mass or negligible mass and a -1 charge, or I mean something with negligible mass and a -1 charge is just an electron. Like that's the definition of an electron. And so you can also use the electron symbol for it as well. And either are fine, and they're interchangeable. Now, a positron is also going to use the beta symbol, because it is also something with a negligible mass. And this time, instead of a -1 charge, it has a +1 charge. So it's basically the opposite of an electron. And so the way you can write it is either with the beta symbol with a +1 and the charge, or an electron symbol with a +1 charge. So you're saying it's basically a positive electron when you write it that way. And again, either's fine. And then the last type of radioactivity is gamma radiation. It has this symbol right here, and it doesn't have mass, and it doesn't have a charge, because it is just electromagnetic radiation, essentially. It's just energy. And so you'll see this will be accompanied sometimes by beta or positron or alpha decay, and it'll release a particle and a burst of energy that's gamma radiation. Sometimes you'll see something like technetium 99 is one that's used a lot in medicine for imaging, an isotope, and it undergoes a nuclear decay. It's unstable, but it decays to it's the same isotope, but it gives off gamma radiation and has a more stable nucleus after that energy is released. And so in this case, we don't actually see a change to the mass, number, or the charge. We just see gamma radiation released alone on its own. And so looking at these in terms of their danger or their penetrating power or their energy, we can see they're different. So alpha particles have the lowest energy and gamma has the highest. And here's our increasing order. We'll call this positron. So an alpha particle can get stopped by a sheet of paper, uh, whereas a beta particle or a positron particle will go through paper and it'll go through your hand and it won't be stopped until it hits metal. A neutron can also be released directly from the nucleus as well, and it'll actually make it through a thin piece of metal, and it'll be stopped by water. Now, gamma radiation will go through paper, it'll go through a human hand, it'll go through metal and water and concrete, and it won't stop until it hits a certain amount of lead. Um, and that lead has to be really thick. And so gamma radiation is the most penetrating of these. And so we think about the danger of radioactive particles by how deeply they can penetrate, right? Like how can it do damage just on the surface of my body, or can it go through me and do damage internally? But the other piece of this is if it goes through you, what is the type of damage that it's actually doing? And so the other piece we track when we think about the danger of these particles is how ionizing they are. And so ionizing is like the damage that can occur to my body, is that if a radioactive particle hits it, that it interacts with a particle and makes it positive or negative, right? Like if an electron hits something, it could react with, can make something negative. If a positron hits something, it could interact with an electron and form gamma particles and essentially eliminate an electron and make it positive. And so we see that while gamma radiation can penetrate just about everything, it doesn't actually ionize that much. So it doesn't make that kind of change. It's just like energy passing through. Whereas an alpha particle is the most ionizing. When that is bombarding your body, it's actually going to ionize the most other molecules that it comes in contact with. And so that's going to do a lot of damage in itself. And so the damage of radiation is this balance between how much does it ionize other molecules versus how deeply does it penetrate through substances, and so how vulnerable are we to it. And they're both really important to think about.